Epistasis is the expression of alleles at one locus that mask or modifies the expression of another allele at another locus. Now, it's important to note that these interactions are between two different genes and not alleles, and that multiple genotypes can lead to the same phenotype. There are 6 different kinds of epistasis. Today, I'm going to show you an example of duplicate recessive. Duplicate recessive epistasis is when identical phenotypes are produced by both the homozygous recessive genotypes. So a different phenotype is produced only if there is at least one dominant allele at each locus. I have created a pathway based on a heterozygous dihybrid cross with the 2 genotypes. At first, there is a red phenotype, and the end product is a purple phenotype, but it can only be achieved if a dominant A allele and a dominant B allele are present. This results in the 9:7 ratio, which is based off of the 9:3 to 3:1 ratio that we observe in simple Mendelian dihybrid crosses. T-bars present in the pathway inhibit the reaction and keep the phenotype from changing, while the arrows, as represented by the dominant alleles, will further the reaction into the eventual purple phenotype. I'm now going to be demonstrating to you how the pathway operates that I showed you earlier for the duplicate recessive epistasis. So we started off with a red phenotype, which is shown here. Now, if a dominant allele A is added, as we saw in the pathway, it's going to result in a red phenotype. Now, the recessive A is going to inhibit it and keep it at this red phenotype, so the reaction will proceed no further. It will stay at that red phenotype. Now, if a recessive B allele is added to this reaction, it's also going to inhibit it and keep it at this red pigment that we see right here. However, if a dominant B allele is added to the reaction, it's actually going to be able to push it forward and create that purple phenotype that we saw at the end. There are duplicate recessive epistasis that don't involve heterozygous dihybrid traits. As you can see, you just separate the alleles and do a test cross between them to determine what the phenotypes will be, since the ratio will no longer be 9:7. As before, you have to have a dominant A allele and B allele to proceed to purple, and only 4 out of the test cross will produce that. The rest will be red since they don't have both of those dominant alleles, which will change the ratio to 12:4 and then reduce it down to 3 red to 1 purple. This is far different than the 9 purple to 7 red that we observed earlier,